Hello, today we're going to be incorporating pandas, basically Python, and statistics together to analyze distributions of a data set. So the data set that we're going to be using is an insurance data set. So let me actually show you what that looks like in 1 second. Okay, so this is what the data set looks like. I got it from Kaggle. It's called insurance.csv, and it's about these individuals and their insurance data. So it's about their personal data and also their insurance data. So for example, their body mass index, the number of children they have, if they're a smoker or not, their region, the charges, so basically how much they charge you for insurance, and their age, and then their sex. So this is the data set that we're going to be using, and more specifically, we're actually going to be taking 3 of the columns or 3 of the attributes, and we're going to be describing the distributions of those columns. Okay, so these are what the distribution looks like. So the first one is BMI, which is the body mass index. Then we have the age. Then we have the charges. So these are what the distributions look like, and we're going to be using SOCV, the statistical method, to describe the distribution. So SOCV is actually stands for shape, outliers, center, and variability. So for the first one, let's go across the board and let's do shape for each distribution, outlier for each distribution, and so on and so on. So for example, the first one, you can see that the shape, I would say it's fairly symmetrical because on both sides you have this kind of the same amount of data. Then in the second one, I would say it's roughly symmetrical because it's not the same as the first one, but you can see that it's kind of leaning towards, like you see like two peaks, but they're kind of symmetrical. And so I would say roughly symmetrical. And the third one I would say is skewed to the right. So now my statistics teacher advised us that it is better to use LI words, so like fairly, roughly, because I don't know if you've heard the saying, but some people say that in science you can never say something is like 100% true. It's always like 99.7% true or 99.9% true. And so you can't really say it's symmetrical because it's really up to interpretation. What was that? I don't know what I just said. It's up to interpretation. So you always want to use like fairly symmetrical or like roughly symmetrical. Okay, so moving on to outliers. So what we're going to be doing is we're going to actually be eyeballing the distributions and trying to figure out if there are outliers and if they're not outliers. And if there are outliers, then what interval are they going to be in? So if you stay until the end, we're actually going to use Pandas to figure out if we were right about our answers. And that's going to be at the end. But the rest of the stuff, like the center and variability, we're actually going to do on demand right now with Pandas because it's short. Okay. So for the first one, for the first distribution, the distribution of the body mass, the body mass indices, or the body mass index is what it's called. I'm going to say there's a possible outliers at 40 to 50 BMI. So that means like you can see that the distribution is actually fairly symmetrical, but there's like 2 little not columns, you call them boxes, rectangles, bars that are to the right that are kind of out there, right? So I'm going to say that there could be possible outliers. So because we're eyeballing it, we're going to say possible. We're going to confirm if that's true or not later with Pandas. For the second distribution, the distribution of age of these individuals, I'm going to say that there are no outliers because if it's roughly symmetrical and I don't see any extreme values, everything is pretty much at the same level. So I'm going to say there's no outliers. Again, we're going to confirm this later if we are right or not. Okay, the last distribution, the distribution of charges, I'm going to say that there's a possible outlier at 60,000, but spoiler alert, we're approximately right. There are outliers, but our interval might not be that right. I mean, it is included, but there's a lot more to it. So for the outlier section, we're going to come back to that at the end and see if we're actually right about these answers, okay? Now, here's a cheat sheet. The third attribute we are measuring is the center for each distribution. So here's a cheat sheet. So if you have a symmetrical distribution, you want to measure the center using the mean. So if it's symmetrical, you want to use the mean to measure the center. If it is skewed, if it's a skewed distribution, doesn't matter if it's skewed left, skewed right, you want to be able to use the median to measure the center. Now, why? The reason why is because let's say you have an extreme values, right? The mean, the average, is extremely sensitive to those extreme values. Extremely sensitive. Okay, that's funny. It's sensitive to those extreme values because remember that the mean is adding up all those numbers and then dividing by the amount of numbers you have. So like, let's say you have like, I don't know, 10 numbers. So you have like a data set that is like 1 through 10. And then you have a data point, like a point that's like 100. Well, obviously that's going to change your average because it's actually going to increase your average. But if you add a point to your data set, that 100, and you want to measure the median, it's not going to change where the median is because you just added like 1 point. You didn't really change the middle of the data set. But your mean takes into account those extreme values. And so it's very sensitive to those extreme values. And if we want an accurate measure of center, of where really the big nuts and bolts of the data lies, we want to use median if it's skewed, because again, if it's skewed, if a distribution is skewed, that means it usually means it has extreme values that are abnormal, right? So yeah, I think that's a good explanation. So if it's symmetrical, then it doesn't have extreme values. Well, usually it won't have extreme values, so you can use the mean, right? And that is why. So for the first one, we know that it's symmetrical. So the center, we're going to use the mean to measure the center. And the way we're going to do that is by using Pandas, because this data set is extremely huge and we cannot do it by hand. It's impossible. I mean, it's possible if you have all the time in the world, but I don't. So we're going to target the BMI column and we're going to apply the mean function, and that's going to give us 30.6634 if we round. So we're going to say that the center of the BMI distribution is 30.6634. Not the center. Well, we can say the center, but the mean or the average body mass index is 30.6634. Okay, for the second distribution, the age distribution, we're going to do the same thing. It is roughly symmetrical, still symmetrical, so we're going to use the mean or the average, well, the mean, to find or to describe the center. So when you do that with Pandas, you get 39.2070. And this means that the average age of these individuals is 39 years old, okay? About 39 years old. All right. For the last distribution, it is skewed. So this is where it comes into play. Again, if you have a skewed distribution, you want to be able to use the median to measure your center, because it can be because the mean takes into account those extreme values. You don't want that. You really want an accurate measure of center, so you want to take the median. So we're going to use Pandas again, and instead of mean, we're just going to use the median function. And we're going to apply that to the column charges. And you're going to get 9,382.033 exactly. And so what that means is that the center of the charges, of the amount that they charge for insurance, is $9,382. I believe it's in dollars because it's an amount that they charge. It doesn't say it in the data set. It says charges because I'm assuming, let's define charges. Charges is the amount of money they are charging the individual for the insurance. So that's what I believe it is. If it's not, let's just go with that definition. Okay, so what's next? So the next thing we're measuring is variability of these distributions. So how do we measure variability? Now, variability also comes into play. It depends if it's skewed or if it's symmetrical, the way you want to measure it. So if it's a symmetrical distribution, you want to use range to measure your variability. If it is a skewed distribution, you want to use your IQR to measure your variability. Now, why? So the reason you want to use your IQR if it is skewed, right? Because if it's skewed, it usually means you have extreme values. So if you have extreme values, think of it as a box plot. If you have extreme values, they're usually going to be outliers, and they're going to be like outside the box and whisker plot. So they're going to be like greater than the maximum and less than the minimum value, right? So that means that if you actually use your range, that means you are taking all of that, the maximum outlier and the minimum outlier, and you're getting that range, and then you're using that to describe your variability. And that doesn't make sense to me in a skewed distribution, because if you really want an accurate measure of variability, you would want to get the nuts and bolts of the data, which is the 50%. So the IQR, if you look at a box plot, is actually the 50% of the data. It's actually the Q1, Q3, and then the median. So Q1, median, Q3. That box of a box and whisker plot is your 50%. That's your IQR. And I think that's a great measure of variability, because it's really telling you, okay, well, it's not really telling you, what am I saying? It's taking the nuts and bolts of the data, of the distribution, what really matters. Sometimes extreme values might just be, like, let's say you have a distribution of like how many times you flip a coin. Okay, well, that could just be out of luck. Or sometimes it just happens, or like some mediating variable or influenced your result that usually wouldn't happen that much. So sometimes extreme values are not that significant. So you really want the nuts and bolts of the data. So the IQR is actually the 50% of your data. So I think that's a great measure of variability. So if you have a symmetrical distribution, then you would use your range to calculate your variability, because again, your range is the maximum value of your entire data set minus the minimum value of your entire data set. And if you don't have any outliers, then that's not really going to affect your range. But if you do have an outlier that's really extreme, that's going to affect your range, because it's literally your maximum minus your minimum. And if all your data is like in the interval of 1 to 10 and you have like 1,000 as an outlier, it's going to be 1,000 minus your minimum value, let's say like 1, right? That's going to be 999 in comparison to 10 if that was your normal symmetrical distribution, and 10 minus 1 would be 9. So 9 and 999. Tell me which one is more accurate to really the distribution, the nuts and bolts of the distribution that you really want to measure. So for the variability, we're going to be using Pandas, and in this case, we're going to be using range because it's a symmetrical distribution, the first one. So what I did was I created a variable called range, and I set that equal to the maximum of that column, so the BMI column. So I did data frame, I targeted the column, then I did dot max, meaning I applied the function, and then I did the same thing for minimum. So that set the value to 37.17. So we can say that the range, or how much the data is dispersed, of the body mass index, how much that is dispersed, the data is dispersed, is 37.17 BMI. Okay, body mass indices, right, plural. For the second distribution, the age distribution, it is symmetrical, so we want to use range to measure variability. So we're going to do the same thing, max, minimum, print range, 46. So again, wait, why is that there? Shouldn't be there. So it's 46. So how would you interpret this? Well, you'll say, okay, your age, how much your age is dispersed by is 46 years, you would say. If your age is dispersed through 46 years, okay? Or your age varies by 46 years. I don't want to get into standard deviation. We'll get to that later. Finally, the last distribution, your called charges distribution. It is actually a skewed distribution. So this slide should have been right here. It's actually a skewed distribution. So you want to use your interquartile range to describe the variability. So interquartile range, you want to use the quantile function. So 0.75 meaning the Q3, because you know that Q3 is 75% of your data. Q1 is 25% of your data, so it's Q3 minus Q1. That's how we get the IQR. So in Pandas, you would just find what 75% of your data is. That's the quantile, okay, and then minus the 25% of your data, which is Q1, and that's your IQR. Set that equal to a variable called IQR, print IQR, and then you get 11,899. So what you would say is that your data varies or is dispersed through 11,899 charges, or it varies, or it's dispersed, where your range of the data is 11,899 charges. Okay. Now, bonus, finding outliers using pandas. So we are going to check if our answers were right. So, okay, so for the first distribution, we said that there could be possible outliers at 40 to 50 BMI. The second distribution, we said that there are no outliers. And then the last distribution, we said that there are possible outliers at 60,000 charges. Okay, so let's check if we were actually right. So for the first distribution, if you take a look at our code, I don't actually think you can see that well. So let me actually present. Okay, you can definitely zoom in, can't you? Hopefully. Okay, so first we have, we read in the data frame. Okay, we figured out the IQR, Q3, Q1. Oh, here's the thing. If you go back to our cheat sheet, if you go all the way at the bottom, you can see outliers. If a value is an outlier, it will meet these conditions. So it will be greater than Q3 plus 1.5 times the IQR, and it will be less than Q1 minus 1.5 times the IQR. So in Pandas, what we want to do is we want to set those conditions. So what I did was I found the IQR. I set Q3 and Q1 equal to their values. And then I said, okay, I created this variable called max value. So what this means, it's the maximum value of the data that it can be any value. So the maximum value any data point can be in that distribution before it is considered an outlier. And then I also did the same thing for the minimums. So the minimum value of the data set before it's considered an outlier. So I set that condition, Q1 minus 1.5 times IQR, etc. And so the maximum value, 47.29, minimum 13.7. So what this means is any values greater than 47.29 and less than 13.7 are outliers. And so then we're going to apply this condition to the data frame to actually see how many or if there are any. And so condition 1 says that any values in the BMI column that are less than the minimum value of 13.7, that's what the condition is. And so we're going to apply the condition to the data frame, get the shape of the data frame now once we applied the condition, and that's going to return this. And so the first parameter represents the amount of rows you have, which is 0, and the second parameter represents the amount of columns you have, which is 7. So we already know that we have 7 columns. We have age, BMI, region, charges, etc. But it's telling us that there are 0 rows, meaning that no values in the BMI column or no instances or rows, whatever you want to call it, fell under that condition, meaning that there are 0 instances where the BMI, the body mass index, was actually less than 13.7. So ignore what I wrote here. It's actually supposed to be less than 13.7, not 47.29. The numbers are switched. Okay, and then we're going to do the same thing. Condition 2, it means is set equal to any values in the BMI column that are greater than the maximum value. So that means any outliers to the right of the data set. So here we actually get 9, 7. So we have 9 instances where the BMI or the body mass index is greater than 47.29, meaning that those are outliers. So we have 9 outliers. Now we said 40 to 50 BMI, that there would be outliers 40 in between the interval of 40 to 50. So the way we can check if we're right is by actually figuring out, okay, well, what are these outliers? So we're going to use a function called value count, and what this does, it's giving us the count of how many times each value shows up in this data frame. So in this case, there's only 9 values in the data frame once we apply the condition. So once we do that, we actually get this function right here. And you can see the column, and you can actually see that the values are 49.06, 47.41, 47.74, but at the end, we see that there's 52.58, we see 53.13. So to make our answer better, we could have said that there are possible outliers at about 40 to 50 BMI, or body mass indices, because it's plural. right? So we were right. There were outliers, but we could have said about 40 to 50 because there are outliers that are greater than 50. Okay. And then here's a modified box plot, which helps visualize the outliers. So you can see that, again, this supports our data that, okay, there are 0 instances where the values or the values in the BMI column are less than 13.7, right? 0, because we don't see any outliers here. But it supports our conclusion that there are 9 instances where the body mass index or values in the body mass index column are greater than 47.29, right? And we have 9 of those values, and we can see them here, okay? For the second distribution, we said that there were no outliers. So we did the same thing. We found basically the maximum value can be before it's considered an outlier, and the minimum value can be before it could be considered an outlier. So any values greater than 87 and less than -9 are outliers. So I did the same thing, applied the condition to the data frame. Then I used .shape to figure out, okay, well, how many rows are in this data frame now that the condition is applied. There were negative, I'm sorry, why did I just say that? There are 0 instances. So there are 0 instances where the individuals were actually less than, -9 years old, because that's impossible. Can't be -9 years old or less than -9 years old. Then we applied the second condition where the age would be greater than the maximum value, which is 87. So in this case, there were, again, 0 instances where the individual was greater than 87 years old, meaning there were no outliers in this data set. So we were right. So here's the actual box plot of the actual column. So these are actually 2 ways to represent these distributions. We would like to use histograms for the shape of the data, and we would like to use box plots for outliers. So you can clearly see it's symmetrical, fairly symmetrical, and there are no outliers, right? Okay, what happened? Okay, so the last distribution, we said that there are possible outliers at 60,000 charges. Okay, so if we look at our data, oh, excuse me, I don't think you got to see the box plot because I was kind of covering it. So let's do that. Okay, so now you can see that, so you can look at it. Okay, but let me present again. I guess I can present here. So for this distribution, we did the same thing, found the maximum value. It was 34,489. Minimum value was -13,109. So basically, any values greater than 34,489, and any values less than -13,109 are considered outliers. So we apply the condition to the data frame. So any values that were less than the minimum value, so meaning any values that were at the left of the distribution, there were actually 0 instances. So this means that there were 0 instances where the charges were less than $13,109, I would say. And that makes sense because what insurance company would charge you negative amount of money? That doesn't make sense. They're not earning money. But then if you apply the second condition, so basically the charges, any charges that are greater than the maximum value of 34,489 would be considered an outlier, and we got 139 instances, meaning that there are 139 instances where the insurance company is charging abnormal amount or extreme amount of money for these individuals. So now we actually said at 60,000 charges. So let's see if that interval was right. So if we use .value counts, the actual method, we can see that in the column, we actually see 49,477. We see 55,135. So we were approximately right. We were right that there were outliers, but we included 60,000. Yes, there are outliers at 60,000, but there were also outliers at 40,000, at 50,000, at 39,000, 35,000. So we want to include those too. So my mistake was that I saw, it's fairly skewed to the right. So I was just thinking that what made it really skewed was that 60,000. But if you think about it, most of the data actually lies between 0 to 10,000 to 20,000, maybe $25,000. And pretty much everything after that is kind of also helping skew the distribution. So those would also be considered outliers. So I would say possible outliers between 30,000 to 60,000, be about, how do you say it? Approximately about, that doesn't make sense. Possible outliers at about $30,000 to $60,000, right? In charges, I think would be a better answer. You want to say about because, again, you don't know specifically the interval. But here's a modified box plot, which helps visualize the outliers. Ignore the change of the square. I don't know. Should it be there? Should be here. Okay, so here's me zooming out. So you can clearly see that the outliers on the right side, there are outliers on the right side, and those are 139 outliers, right? While on the left side, there are no outliers because no one is being paid less than negative $13,109, which is basically the minimum amount of money that you would be charged for it to be considered a normal charge, while anything less than that would be considered an abnormal charge. But in context, anything less than 0 would be considered not logical because, again, an insurance company would not charge you $0 or less than that. And what else? And basically the same thing on the other side. So the maximum value was what? 34,489. So those basically are outliers. So anything greater than that would be considered extreme or abnormal or not normal charges, right? So anything greater than $34,489 as a charge would not be considered normal, okay? So here's a cheat sheet copy of the way you should use these attributes and how to measure certain attributes. So that's for your reference, and I'll be posting any links. I believe the data file link on the description box below. If you want to see how I made the distributions, I'll be posting that, like the distribution graphs, I'll be posting that as well. And I don't know if I'm missing anything else, but I think that's it. Anyway, have a great day. I'm going to go now. Okay, bye.